So in this section, let's talk about confidence intervals for one population mean when the population standard deviation, that's the letter sigma right there, is known. Now in this technique, we're going to be talking about a technique that depends on knowing that we already have a normal distribution and that standard deviation for the population is known, which is not such an unusual situation as you might think. Here's an illustration of a normal curve, and we've talked about these normal curves now in the last few chapters, and approximately 95% samples, if you recall by the empirical rule, fall within 2 standard deviations of the mean. What does that really mean? Well, if we looked at our samples here, we might see that, well, if we were to build a curve, a normal curve that contained our population, that contained all of the distribution of all of those values within our population, we might see that 95% of all of the data that we could get for our sample would fall within 2 standard deviations. That's positive 2 standard deviations of the mean and 2 standard deviations above and below. Right here we see that where population mean, mu, is going to be in our standard, in our sampling deviation of the population, right? Our sampling distribution, recall, we take 2 times the standard deviation divided by the square root of the sample size. And if we add or subtract that, we see what's going to happen. About 2.5% will be less than our mean, and 2.5% for a total of 5% will be above our mean. This, by the way, is a very important idea. We call that total probability that falls outside of our sample mean, we call that alpha. That's our alpha level here. And our alpha level in this case is 0.05. So we're saying that 5% of all of our population samples could possibly fall outside of that 95%, which makes sense. It has to add up to 100%, right? So when we talk about this alpha number, we talk about this level of confidence, what we're really doing is we're saying that if we take 100 times 1 minus that alpha number, so 1 minus 0.05, now right here, 0.05, that's going to give us that 95%. Right? Well, what does that mean to us? If we were to choose, 95% is sort of an arbitrary number. We're saying, okay, well, we're interested in saying when 95% of the data falls within those 2 data points, but what about any other percentages? Well, this number right here, z alpha over 2, expresses the actual z value. Recall it, z is the mean minus the standard deviation divided minus the population mean divided by the standard deviation, and that gives us a position, right, a standard position of the number. So we take that z alpha over 2. If alpha is 0.05, right, alpha over 2 is equal to 0.025. There it is, right, alpha divided by 2, and 0.025. So whatever our percentage is that we're interested in, right, this is our level of confidence. 1 minus alpha. So 100 times 1 minus alpha gives us a percentage of our level of confidence. And alpha over 2 gives us the percentage that we have a mean that's going to fall outside of this normal distribution that we want. All right, so how do we calculate this? It's actually a very straightforward method right here. For whatever 1 minus alpha level confidence we want, we're going to use table 2, and that's our standard normal distribution table, to find z alpha over 2. All right, and I'll outline some common ones that we use right here, but essentially we're going to build our confidence interval by taking the sample mean minus our z number times standard deviation divided by the square root of the sample size. So it's plus or minus that number. We call that number right here, this n number right here, our margin of error. That margin of error tells us how big the sample's going, how big our error away from the population mean could be from our sample mean. And then we're going to interpret that confidence interval. So let's just go through a basic example to show how this works out. Remember that we're going to take our mean minus the standard, our error, right, our maximum error of the estimate, we call this our margin of error sometimes. We're going to take our mean minus the margin of error and our mean plus the margin of error, where we take that margin of error to be the z alpha over 2 times sigma, this population standard deviation, divided by the square root of n. Some common values that we use here in our calculation are going to be right here. For our 95% level, the number that we actually get from table 2 is going to be 1.96. That 2, when we estimated 2 in our empirical rule, was an approximate number. 1.96 rounds up to 2. But for exact values in doing calculations like this, we're going to use 1.96 when we mean for our z alpha over 2 when we want a 95% confidence level. Here's an example. Let's say that we took a sample, whatever it is, and I found that our mean was 25. We took a sample size of 36, and our standard deviation for the population is known to be 3. Well, to find a 95% confidence interval for the population mean, what we're going to do is we're going to find our margin of error first. In this case, z alpha over 2, 1.96, is multiplied by 3 divided by the square root of 36. So we come up with 0.98. Well, this margin of error is 0.98, and this means that the estimate for our mean will fall within 0.98 of the sample mean. What we're saying right here is that if we take our sample mean of 25 and subtract 0.98, that's 24.02. Or we take our sample mean of 25 and add 0.98, we get 25.98. We mean that we have within a 95% level of confidence that the population mean will fall between those two numbers, 24.02 and 25.98. We consider this our interval estimate, or our confidence interval, for this particular population. All right, that's just using the numbers right here. Let's try and put a little bit of a context to all of this. When we use the one mean z interval procedure, how do we know when to do this? Well, for this particular procedure, we're going to say the following. If we have a small size sample, we know that sample size is less than 15, let's say, then the z-interval procedure should be used only when the variable under consideration is known to be normally distributed, or at least very close, right? If we have a very small number in our sample, this is very important. If we have a moderately sized sample, somewhere between 15 and 30, some of the same problems involve themselves. The z-interval procedure can be used, though, unless the data contains outliers or the variable under consideration is far from being normally distributed. If we were to go through and check it out, we might find that that sample does not represent a normally distributed variable. That's something that we'd have to check, and we'll look at a different procedure of how we handle that. But if we have a large sample, size 30 or more, basically the z-interval procedure can be used pretty much without restriction. For larger size samples, remember that we found that that distribution ended up getting closer and closer to the normal distribution in Chapter 7. So that's what we're relying on here. Now, if outliers are present and their removal is not justified, we should compare the confidence intervals obtained with and without the outliers to see what effect they have. But if the effect is substantial, we might use a different procedure or take another sample if possible. And again, this is going to depend on what we talked about in Chapter 7 on our sampling distribution of the mean. But if outliers are present, but their removal is justified, the data set for which the z-interval procedure is appropriate, and the procedure can be used. Now, having said all of this, there is a key idea that we need to know. This fundamental principle says this: before performing any statistical inference procedure, such as finding a confidence interval, examine the sample data. If any of the conditions required for the procedure appear to be violated, don't do the procedure. Instead, we're going to use a different, more appropriate procedure if one exists. And we're going to talk about an alternative procedure in the next section. So let's talk about one like this. Here we've got a table that shows the ages and years of 50 randomly selected people within the civilian labor force. It's known from previous research that the standard deviation for the population is 12.1 years. So what we're going to do is we're going to enter this data in Excel, And then we're going to determine the margin of error for a 95% confidence level interval. We're going to find a 90% confidence interval for the mean. And then we're going to compare those intervals and see what they say. And we'll try and come to some conclusion. What's the relationship between confidence and accuracy? What could we say about those things? So we've gone to Excel. And I've entered in the data right here. You should take a moment, make sure that you do this for yourselves here. But there are 50 data points we can see. Let's go ahead and find our mean. The standard deviation, the population standard deviation is given. So our mean, you recall that our procedure was that we hit average and enter that in. So we're going to take our average starting at A2 and going to A51 in this data set right here. Doesn't like the way that I spell it. Aha. There we go. And we find that the mean is 41.38, right? Now, right now, I've got no confidence level because I haven't built a margin of error. So how am I going to get my margin of error? Well, let me show you a trick on how we can do this using Excel. That same calculation that we showed before is applicable here, except that in Excel, we can use a command called confidence.norm, N-O-R-M. Okay, so when we enter that, what do we want? We want our alpha level. Now, if we say it's a 95% confidence level, remember, that means our alpha level is 5%, and we enter that as a decimal, 0.05. Our standard deviation, well, that's given to us, 12.1. Notice that we don't have to enter the mean, the actual mean that we got from our sample in this to get this confidence level, right? We're getting our margin of error. But we do enter the sample size, and in this case, the sample size is 50. Whoa, look at that. That's changed, right? So our confidence level right here for 95% gives us a margin of error 3.35 years, which means that our confidence interval, 95% confidence interval, will be somewhere 38.03 years to 44.73 years. All right, that interval where 95% confidence will contain our actual standard deviation. It will actually contain our mean age for the population. Let's try it for a 90% confidence interval. Again, we're going to enter the same command. It's confidence.norm. And we enter our alpha level. In this case, if it's a 90% confidence level, that means that we have a 10% alpha level, right? 100 minus 90, that's 10%. So we enter in 0.10 in decimal form. We enter in our standard deviation. Again, we were given 12.1 for the population standard deviation and our sample size of 50. All right, let's see what happens here. Look at that. The numbers go 38.56 years in this case to 44.19 years. All right, well, let's take a look at our slide here and what this means. Remember that our margin of error basically is going to be that z alpha over 2 times sigma divided by the square root of n. That is our standard deviation for the population by the square root of our sample size. We designate that using the letter E. Thus, here's our calculation. So let's show this for our two calculations. Our margin of error for 95%, if we did this by hand, would be 1.96 times 12.1 over the square root of 50. We come up with 3.3439 years. In Excel, yeah, 3.3539 years. So that's actually right on target. We found that our margin of error for the 90% confidence interval, we'll use the number 1.645 for that, times 12.1 over the square root of 50 comes out with 2.8147. And if we check out Excel, sure enough, right, 2.8147. Sure is. All right, so that's our margin of error. Well, what do we do with this margin of error? Well, remember that our margin of error is going to give us our sample mean minus the confidence level, our error, margin of error, and plus our confidence margin of error. So for our 95% confidence level, we can see that 38.03 to 44.47, this is an interval that's going to contain our standard deviation, our population mean right here. So our population mean should be somewhere between these two values. And we use mu for the standard, for the population mean. Right? So somewhere between those intervals will contain that population mean. We notice, by the way, that that interval becomes a lot smaller when we use a lower confidence interval. In other words, we're only 90% confident that the mean will be between 38.57 and 44.19 years, right? So for a fixed sample size, decreasing that confidence level actually decreases the margin of error and therefore improves the accuracy of the confidence interval estimate. We have a lower confidence, but we have a tighter estimate. Making a larger confidence interval should make sense, actually means that we're going to have to cast a wider net to actually catch the population standard deviation. But we're 95% confident up here that that's what's going to happen. Well, we can also affect what happens by changing the sample size, right? I mean, let's take a look back at that spreadsheet right here. Let's say that we changed the sample size. Let's say that we made it 25 instead of 50. What would have happened? Well, in this case, let's just experiment. Let's put in our confidence.norm. Right here, here's our command. We want that alpha level of 95%, so 0.05 for our alpha number. That's what we put in. Our standard deviation given 12.1, but this time let's change that sample size to 25 and see what happens. And we can see that we have a much wider, look at that, we have a much wider sample size. Let's see that I've entered everything incorrectly here. Oops, 12.1, that might help. 12.1, let's see, there it is. All right, 4.73. So we see that in comparison to the 95% level, that margin of error increases. That gets a much larger margin of error by having a smaller sample size. But this should, again, make sense based on what we talked about in Chapter 7. We see that by increasing the sample by decreasing the sample size, we have to have a much wider margin of error to contain our possible population. So for a fixed confidence level, increasing the sample size decreases the margin of error and hence improves our accuracy for our confidence level estimate. If we have a larger sample, we're going to have a better result. Stands to reason. All right, last bit of this is, well, if we know that we can get a certain margin of error, we can find our margin of error based on a sample size. Do we know what sample size we need to get a certain margin of error? And the answer is yes. We can estimate our sample mean within a certain population by finding a certain sample size. Sometimes we might have to find a very large sample size, right? But the procedure is pretty much the same right here. This formula, n equals z alpha over 2 times our standard deviation for the population divided by the margin of error squared, is developed algebraically from our margin of error calculation, right? There's a little bit of algebra involved right here. For the confidence interval, though, if we have a given confidence interval, we can find the sample size that's needed to obtain it. And as an example, let's consider our estimating our mean age for our population civilian labor force. And let's say we want to determine the sample size needed to have a 95% confidence interval that the population mean is within 1/2 a year of the point estimate. In other words, we want to get really, really accurate. How large a sample do we need to get to be within 1/2 a year of the actual population mean? So let's recall that our standard deviation was 12.1 years, and let's use that. If we put in the numbers right here, 1.96 as our z alpha over 2 times 12.1 and divide that by 0.5, right? Our margin of error, we wanted to be 0.5. And then we square that number, we come up with 2,249.7946. Well, what does that number really mean? Well, remember, we can't have 0.7946 people in our sample. Clearly, we have to go by whole numbers of people. So we round that up. And every single time you use this calculation, always round up. There's a little bit of caution right there. Always round up to the nearest whole person. So in this case, we should round that sample to 2,250 people. And even if our sample said 2,249.1, we would still round up to 2,250. Well, the next question, of course, is, well, what would our 95% confidence interval for the mean mu look like if the sample size determined in Part A has a mean age of 43.8 years? Well, if that were the case, then using the information we just found, we're going to add and subtract that margin of error of 1/2 of a year, and we would find our confidence interval of 43.3 to 44.3 years.